All right. Well, as long as, and David, let me just check that you're ready.
I am. Thank you. Good morning.
Because then, David, I get the pleasure to introduce you. So when the Corporate Innovation Program team asked me whether I'd be willing to introduce David, it was a request that I accepted with tremendous pleasure. So Professor Dava Newman's been a long time colleague of mine here at MIT. And I think, David, I'm right in saying that probably one of our first conversations was one that was took place sitting on the stage at MIT graduation together. And anybody who sat through MIT graduation will know that that's actually a pretty long conversation. That takes quite a long time. And since then, I've been lucky enough to engage with Dava through a series of collaborations and conversations, including around the technology and policy program, innovation leadership. Dava is the Apollo Program Professor of Astronautics at MIT. She's also a faculty member at the Harvard-MIT Division of Health Science and Technology. She focuses on space, how people can be healthy in space, but most as recently also thinking about how we see and understand our own planet from space, how we can take lessons from the space program and advance them in our work on climate and the environment. Dava is way more than just an ivory tower academic, as she knows how to bring innovations to impact. She's been principal investigator on 4 spaceflight missions, including the Space Shuttle, Russian Mir space station, the International Space Station. If that's not enough, she's also known for the revolutionary biosuit, a planetary spacesuit, which is probably one of the coolest things. It's also in the Boston Museum of Science. And probably relevant for today, at a wider organizational level, Dava served as NASA Deputy Administrator. Who's actually the first female engineer in that role. And in doing that work, she was awarded the NASA Distinguished Service Medal. So with that, absolutely my pleasure to hand over the floor to Professor Dava Newman.
Thank you so much, Fiona. How's everyone this morning? Oh, it is such a pleasure to be with you. I'm super excited for this discussion. So with your permission, we'll zoom through the solar system and then end up back down on Earth for what I hope is going to be a really interesting discussion. So let's get started. Okay, everyone can hear me? I want to do a sound check and then a visual check because I have lots of visuals. Okay.
Looks good to me, Dava.
Thank you. So I'm an explorer myself. And what's exploration? What's it all about? Scientists and engineers, it takes everyone. We basically have 3 fundamental questions in exploration. Are we alone in the universe? Are there other habitable planets? And is there life? So those are pretty big, audacious questions, but the challenge is never too great. And I want to tell you what we're finding in terms of some of our scientific discoveries, some of our technologies to really unravel these 3 questions. You've just watched an image from our Hubble Space Telescope. If anyone online is 30 years or younger, your entire lifetime, Hubble has been exploring, asking, searching the answers to these questions, are we alone? Are there other habitable planets out there? So most of my students then, of course, are under 30. And it's pretty amazing that, again, this is space explorations for the long term in terms of all of our exploring. Everyone's heard of exoplanets? I need some audience interaction, some hands raising or not. So in this search for extra planets, thank you for participating, Dave, appreciate it. Keep everyone awake here. But the artists paint the pictures, what do exoplanets look like? Where are they? These are 10 to 100 light years out. So here's the artists when we found Kepler 16b. And, move over Luke Skywalker, I like to say, because it is a binary system, 2 suns, so you get 2 shadows. But on the right, those are real images from TASS. That is the MIT exoplanet survey system. So every day we're getting images like this of the real exoplanets. So it's just amazing to, again, the vastness and what's our place in this vast solar system and universe, fundamental exploration of all there it is to explore. I'm going to zoom in to the solar system. Wish I had more time with you, but we're going to kind of focus in. This is just, we are at Jupiter today, in case you don't wake up every morning with your coffee and say, what's happening on Jupiter today? What about that red spot? What about that storm that's raging? This is definitely what's called the Juno mission. It's after the goddess of Jupiter. And I'm showing this beautiful image. It looks like art. It looks like art, but this is really high resolution images of Jupiter that we see today. And I'm not sure how big your screens are, if you can see this, but in the image on the left of Jupiter, that red storm, I actually have photoshopped the Earth to scale inside. This is the largest solar panel spacecraft that's ever flown, and the furthest that we've put a solar powered spacecraft to explore Jupiter's moons. Zooming in a little bit, we could talk about all 100 science missions that are going on today, but I want to come down to my sweet spot to take a look at Earth, the Moon, and Mars. Take a look in terms of habitability, some of the technologies that we're developing, talk to you about kind of an innovation framework. This is another, again, scientific but beautiful image from our Discover mission. Discover is out at the Lagrangian point. That's halfway between Earth and the sun. So it's 1.6 million kilometers out, and it's looking back at Earth. It's looking back at Earth saying, Earth, here's what's coming your way in terms of solar wind, solar radiation. And then Mars, half the size of Earth, is my second favorite planet. That's where we're going to get ready to send humans in the future. First the Moon, next step, and then Mars. But again, I do think of Earth as spaceship Earth, and we'll spend the last part of my talk talking about taking care of the planet, and as an aerospace engineer, how our satellite data, how our images really are accelerating possible change for spaceship Earth. So we have been to the Moon. We're going to get humanity to Mars to be interplanetary. But again, there's always this reflection, I would say. All of our searching out into the solar system is to reflect back here on Earth, use our technologies also for Earth purposes. So the vision and the passion to explore is great, but also trying to always bring it back home to see what the relevance is of our science and engineering. So I want to put up this graphic for you to kind of frame how I'm going to talk to you about innovation in 4 quadrants, if you will. So if you look at the green area on the bottom, I call that existing technology in an existing organization or an existing business model. That's about 80% of where I call it continuous innovation. Just doing something great every day, doing something, being on it, trying to do your best work every day, just continuously innovating. People, as an engineer, we get a lot of pride out of it. How can I do something better today? But just continually trying to innovate. Doesn't take a new business model, doesn't take a lot of new technology. So that's about 80% of where innovation comes from. Then if you go over to what's on the left side, the red, I'm going to call that disruptive innovation. And that's where we need a new business model. We need a new organizational structure. We're going to use the same technology, but we need to do business very differently. When you flip over to the right side, the darker blue, now this is what I call revolutionary innovation. What about revolutionary technology? I'd love to do this at MIT. Can I invent new technology? This really breakthrough technology. I can do that within my own business organization. I don't need a new business model organization, but this is a big technology push. Up top, the light blue, that's really hard. That's what I'm going to call transformative innovation. And that's, I need a new business model and I need new technology. So I have to transform not just the organization and business, but I have to transform the technology. So doing both of those transformations together is hard. Those are the big challenges. So I want to walk you through what I think are some fun examples to put this framework into use. This is just a visual history of when I went to NASA. I was there from 2015 to 2017. Of course, NASA is innovative, but it's a huge bureaucracy. Some of you might come from very large organizations. Even at MIT, we tend to think about our bureaucracy. We want to get things done fast. We want to innovate. We want to be creative. Well, there were these barriers to innovation, and they had been studied. What's slowing people down? So they had been articulated way back, 2011, 2012, and then thinking about, well, what do we need? Some creative labs, some iLabs, some innovation labs, some creative spaces. Do we need a skunkworks type of idea? So, where do people innovate in a physical environment? Where do people do their best work? How do you unleash the innovation from people? And then in the middle, I said, but we actually need culture change. Came to NASA, you say, how do you change the culture? Again, how do you become what I just simply call the yes zone? Don't get caught up in the, no, we don't have the funding. No, we don't have the charge code. No, no, say no, just first say yes. How could we get there? We might not have the resources, but how could we get there? Let's how. And that really is a culture change. Show you a good example of that coming up. And then basically putting it up onto the senior management and say, are you gonna propose, that NASA in this case could be very innovative. What opportunities, what are you going to really do to change culture, to accelerate innovation? And then also from the bottom up, try to bubble it up. So it's kind of a bottoms up and a top down approach to see if we could get this done. That's just a little schematic. I want to go back to that framework. We called out throughout the agency and said, give us your examples of innovation. Well, guess what? In no time, in a week or two, we got 100 examples, 100 promising practices, because everyone was innovative. They were just dying to let us know what they were doing. NASA's a large organization, as you know, 18,000 civil servants at the time, and 9 centers. So the great thing was from different organizations, we got their promising practices. That was a huge step, just to celebrate what people are doing, and trying to communicate that, kind of unleash that, and give them again the yes power, kind of enable them. So, and I also gave an award for failure. Because talk about culture change, when people, were walking around with t-shirts that failure's not an option, that's a very risk-averse culture. That it's not causing people to kind of go out on a limb to try to even think that they're empowered to be innovative. So it was called Lean Forward and Fail Smart. I have to say fail smart, but what it was to say, no, can we really have a different conversation? Can we change the conversation and celebrate creativity and innovation? I'm hoping that this video will work for you. It's a lot to ask. Is that okay? I think it might be working, but there's nothing like seeing rockets blow up if there's not people in them, right? So this was send in all of your suggestions, and let's try to get like a lunar lander. We're going back to the moon and taking a look at that. Well, you never want to see a spacecraft go up in fire in a flame like that. But of course, when you empower people after winning the award, guess what? Then they nailed it. This is not a fire. This is a night flight. So of course, in the failures, we learned so much more, and you were going to get it right, as designers and engineers. So again, just empowering them. Now that was actually a successful flight after the end, after saying just iterative design, do it. But again, putting it out there and celebrating it in terms of just continually try to keep at it, try to innovate. So we're going to give an example now of disruptive innovation. Again, no new technology here, but doing business a very different way. And so some of you are probably pretty familiar, I hope, with NASA's public-private partnerships, saying, okay, now we're going out to the commercial sector and just buy services. NASA doesn't need to own any of that. NASA doesn't need to operate all those because that's very, very expensive. So there's commercial cargo. Now, the company is all listed here, as well as international partners delivering cargo to space station. We've been living and working on space station for 20 years. We're just celebrating the 20th anniversary this month. And just recently, hopefully you saw this summer, SpaceX taking the astronauts up. We haven't had astronaut launches from the US in many years after we retired the space shuttle, and Boeing has its Starliner. So this was incredibly disruptive, saying, no, we'll buy services, we'll let out fixed price contracts, and we'll buy these services from the commercial sector. Because it's the right thing to do, because it's a new organizational structure. It's a new business model for NASA, if you will. So really powerful. I mentioned space station, and I wanted to just show you that 20 years. So this was Scott Kelly who did the 1-year mission, and you see Karen Niebert there. The thing about space station is it's probably the best international model we have of 5 main partners: NASA, Russia, Japan, Canada, and the European Space Agency. That's just 23 nations in itself. So those 5 main partners getting together, an international model to all work together for 2 decades. And the most important thing is over 100 nations have sent up experiments doing science, like I said, off the Earth, but for the Earth. Really, I think it's one of the best international models we have. Okay, now I want to spend some time with you. I'm talking about technologies. You're looking at innovation. You came to MIT, so I could tell you a lot of different things about technology and really pushing the technology within our own organization. So I'm going to tell you about some of the technology that we're developing at MIT right in my lab, and it has to do with keeping astronauts healthy and safe and well. Now, we've been to the moon. These are the lunar spacesuits. These are what I call my bloopers. Incredible technology for the time. The spacesuit is the world's smallest spacecraft. Okay, you have to design all of the systems of a normal spacecraft, and you have to put it around the body, provide pressure, provide oxygen, provide all those systems to keep someone alive. Then if you look in the middle and to the right, this is the current systems. They're big gas pressurized suits. They weigh about 140 kilos. I'm going to put you in almost a 300-pound spacesuit. So that's not what I dream of when we get back to the moon. So what could we do? What could we do differently? You have to pressurize someone. So in that big gas pressurized suit, again, it's about 30 kilopascals, about a third of an atmosphere. We said, maybe there's another way. Maybe we could put the pressure directly on the skin. So that's the concept of the biosuit. You have to keep someone alive, pressurize them, put the pressure directly on the skin. And then you would have a very lightweight system, a very mobile explorer. So I'm going to talk to you a little bit about some of the technology that we're developing and working on even today. So if you want to, first you have to think about it differently. You have to obey physics. So we're just trying to think of a second skin pressure producing suit. How could we do that? Well, these are nice images, but it's a lot of the mathematics behind. We're studying the patterning of how we would essentially design this suit. And we won't go through all the three-dimensional math here, but it's coming up with a pattern that we could afford full mobility and come up with this patterning and the materials to get it done. So put you in a laser scanner, very into the millimeter level, take a look at, these are strain maps in terms of circumferentially, longitudinally. Again, I'm watching you move and I'm looking at 40% strain in terms of how do you bend. If I give you full mobility, we're really mapping that in quite some detail. And then coming up with, well, then what's the pattern? What material properties do we need? And what's the pattern to go ahead and come up with this suit? So this is digital image correlation is what's this called again, looking at all the strains and the stresses and the patterning that we can essentially come up with a suit that literally moves with you, moves 100% with you. So that's where the technology push is. It continues. If I can determine what the material properties are, give you kind of this passive elastic, this very, very mobile suit, then there's room for active materials. So now I'm gonna put a push in the active materials because they'll help cinch it up, if you will. They'll apply a little bit more pressure. With the patterning, with typical materials, we could get about 20 kilopascals. Our design goal is 30 kilopascals. So in this case, we're using some shape memory alloys. That's a nickel, titanium, muscle wires, sometimes they're called, and kind of cinch it up a little bit more. Today in the lab, what we're looking at is something called a shape memory polymer. Well, what's that? Again, it's an active material. Say if my suit is on, you're trying to put your suit on, it's tight, but you can put your arm in it without just trying to get dressed very quickly. The shape memory polymer basically can be about 1 centimeter wide, and it triggers on temperature. And if you know space, it's very cold on Mars or the moon. So then I get to a trigger temperature and it would essentially it would constrict you and apply pressure. So you stay in the constricted. So we're looking at these shape memory polymer materials that are triggered by temperature. So it's an active material, but we can use it to our advantage of, we call it donning and doffing in the space world, putting on your clothes, taking off your clothes and doing that. So this is ongoing work right now. I've been talking quickly, but just about the pressure production. You know, what are the technologies we can think of? How can we really push the technology for a new capability to keep humans, astronauts well? We also have to worry about life support. You know, your oxygen tanks, and redesigning that, not the 140 kilo suit, making you much more like an Olympic athlete or an extreme camper, you know, trying to go with your mobility. And then also what coat are you gonna wear? What thermal protection in the extremes of space, plus or minus 200 degrees Celsius on the moon. I really have to protect you thermally and from radiation, which has never been done in suits before. So we're taking a look at that. First, we look at it from the design perspective. Then we look at it from the material perspective. We're planting some aerogels. We're looking at some nanotubes. I'll tell you a little bit more about that. We've just developed a new material, and what it is, it's polyethylene, which is plastics, a boron nitride nanotube, and an aerogel. And we fabricate that in terms of these nanotubes, has huge thermal protection as well as possible radiation protection. So it's very exciting. This is work that's just in the lab now. Again, taking aerogels, which are almost massless, I mean, literally almost massless. And then we're making these new, what are actually called boron nitride nanotubes. And you have a nano sheet, you have a nanotube, and then basically we fill those gaps, if you will, with hydrogen. And it's very light, but that actually has a possibility to help protect against some of the radiation. Specifically in this case, we're looking at the moon. We're just learning about the lunar radiation environment, and we need to protect the spacecraft, the landers, our electronics, and some protection for the humans as well. But again, we want a lightweight, very mobile system. So this is a big technology push. It'll hopefully help us to do our exploration in the future, to get people back to the moon, to go onward to Mars. But I just wanted to do a little bit of a deep dive for you in terms of some of the technology we're working on today in the lab and the capabilities that we're working on. Again, kind of a big technology push, the revolutionary technology when it comes to innovation. And now that's not even the hard stuff, even though that's almost 2 decades of work. The hard stuff is, again, doing 2 things at once, and really thinking about innovative technology transformation, as well as a new organizational model. So lots of things we could talk about, expanding human presence even further into the solar system. That question about, is there life, and where will we find it in the universe? And I also want to talk about really understanding global climate change as well. So I'm going to keep talking to you about a little bit of examples in terms of, again, we need a new organization, we need new ways to think about things, and we definitely need new technology to go explore what we call ocean worlds. And I put Earth right in the middle, still very unexplored when we talk about our oceans. And then I like this because it's to scale. These are our moons that Enceladus, you might have heard of. I hope you've heard of it. It's a moon of Saturn. After Mars, then it's probably the best place in the solar system. Go look for the building blocks of life. I don't know if you've been to Old Faithful and Yellowstone Park. I'm from Montana originally. And so when you get to Enceladus, out of its south pole, it's spewing hydrocarbons. It's spewing the building blocks of life. It's spewing out chemistry that we say, we're looking for water. Look for life. We say, follow the water. So we're looking in the solar system for where are the building blocks of life. The hydrogens, the sulfurs, the carbons, where is that chemistry? Enceladus is really promising. Europa is a moon of Jupiter. It's an icy world. It's an ocean world. We know it's filled with, it has ocean water. It's just below kilometers and kilometers of ice. So it's a great place for us to go to explore. Can we find the evidence of life? And all of these moons, Titan, Triton, Ganymede, Callisto, these are all ocean worlds. We know they're made up of oceans. So where there's water, again, follow the life. Will we find the evidence of life quickly and within the next decade? These are all really good bets, and missions to Enceladus and Europa now in terms of, again, the fundamental questions about life in the universe, existing life in the universe. Past life is what we'll probably find on Mars, given Mars and Earth are sister planets, both 4.5 billion years old. And Mars probably was warm, wet, and wonderful, I like to say, but it lost its atmosphere. Today it's left with 1% carbon dioxide atmosphere. So studying these amazing ocean worlds really informs us, as I said in the beginning, about life here on Earth. And that's what I'd like to kind of circle back to now quickly. Because what's all of our science, what's all of my technology for if I'm not trying to also help humanity, help my neighbors? So as an aerospace engineer, we have these 20 satellite constellations looking down on Earth. So I call it Eyes on Earth. And I actually quote Bucky Fuller here, kind of the philosophy of what can we do to help life here on Earth as a scientist, engineer, to just make the world work for 100% of humanity. So what I'm showing you are some supercomputer simulations. I'm going to show you these individually in a minute. But what about weather? What about extreme climate? What about the oceans, the currents? We really have to look at Earth in terms of all of Earth's systems, our ocean systems, our land systems, our air systems. They are definitely all connected. So I want to show you a little bit more about the details of the research here. So Earth DNA, we call that data into action. Just some statistics about how we're doing, how we're taking care of Earth, how we're living together. As you probably more in terms of the unused plastics now that we're all living in the pandemic and COVID. And really have to worry about our populations and biodiversities. Over 4 decades have declined over 50 or 60%, over 60%. And we know this, getting to 1.5 degrees temperature, it's bleaching our oceans. I'm an avid diver. The underwater oceans, again, really life's vital signs. The Earth is, breathing, living system. So I like to call it Earth's vital signs. So I'm going to show you some of the scientific data that we have, again, from a holistic, from a zooming out, looking at spaceship Earth, because all of us are here together. This is our lifeboat. So I'm going to show you this is 140 years of temperature data. Blue is 1 to 2 degrees Celsius below a 30-year running average. And yellow and orange are 1 to 2 degrees hotter. We're already at 1 degree C average. And you can see the 1950s, 1960s coming up. You can see the decades clicking by. You can raise your hand when you're born if you want. 70s, the 80s, the 90s, and then we go into 2000s, and now this is the last decade. It's hot. This is the data. These are just simply the scientific facts. Again, how is Earth doing? What are the vital signs? I want to show you carbon dioxide as well. Carbon dioxide in kind of 3 dimensions. This is greenhouse gas emissions. These are human caused as well as natural disasters, fires, but this is primarily from humans. This is all of us living. We don't want to be above 400 parts per million CO2. This is, I'll show you a year in the carbon cycle. Blue is going to be below 400. We'd like to see blue. Yellow and orange are going to be above 400 parts per million in terms of carbon dioxide. So I like this supercomputer simulation with all of our satellite data. Look at 5 kilometers, 10 kilometers, 15 kilometers. I'm showing it up to 20 kilometers if you go up in altitude. It's pretty striking. You'll see all of the CO2 emissions. Again, literally, this is the trapped greenhouse gas emissions. And so we can see them, we can monitor them, we can measure them. The continuance, what about ice? What about sea level rise? Again, the oceans connected to the land, connected to air. So the Greenland ice sheet and the Antarctic ice sheet hold 99% of the world's water trapped in ice. Those 2 ice sheets are critically important. And up north to the Greenland ice sheet, it's changing rapidly. We measure it again with satellite data, our ISAT data. We fly over with aircraft. We have sensors on the ground. And you can see some numbers there. Just in 1 year, we lost over 400 gigatons of ice. It's not just that we're losing the glaciers, we're looking at the velocity vectors and how we're losing the ice. Why is this important? For the Greenland ice sheet, that means 6 meters of sea level rise. If the Antarctic ice sheet, remember Antarctica, it's a 10,000 foot continent, right? 10,000 feet of ice, or 3,000 meters. That would be 60 feet of sea level rise. In the last 20, going on 30 years, we've had getting close to 30 centimeters now, 30 centimeters. But Greenland, 6 meters. So this is what we're studying, and we have all of this data. We know the scientific facts. I want to kind of show you this eyes again from our satellite data from space. This is what we see when we take our satellite data, we combine it with the physics-based climate models to give people the data. not interpreting the data, I'm just showing people what the data is. So in this simulation, this view, you're going to see three things. You're going to see the ocean currents. You're going to see smoke. You're going to see smoke on land, trying to connect, North America to Europe. And then you're going to see the dust coming off of the Sahara. So you'll see smoke, you'll see the ocean currents, and you'll see the dust. So it's literally looking through that atmosphere, looking down on Earth, looking at Earth's vital signs and systems. This is just for a month in 2017. Hurricane Maria came up. Look at all that dust coming off of the Sahara. You can see in the northwestern United States, all the forest fires. And then take a look at Europe. This is October in 2017, the Iberian Peninsula. This is when Spain and Portugal had their worst fires ever. And Ophelia, very strange pattern. Ophelia came right up the west coast of Africa and smacking into Europe. Usually they go over to North America now. But again, just kind of the eyes on Earth, kind of looking at the important scientific data, trying to combine it's really complex systems. It's all the Earth systems and these vital signs. So what can we do about it? That's the scientific data. How do we take this data? How do we give it to business leaders to, it makes business sense, for economic going forward, how are we sustainable? What do governments do? What about policymakers? And what about just individuals, just the public? So we're really looking at this across all spectrums and used a lot of artificial intelligence. So what can we do with all this data? How can we visualize it? How can we turn it into actions in the future? First, it can inform people, but then secondarily, we have to think about bringing about behavioral change. So I want to kind of show you some very, very recent data. It's, I think I can do this. It's basically using artificial intelligence, machine learning, taking images. So then we created the first photorealistic. Think about this as satellite imagery of the future. If I show you your house or your ranch or even the urban environment, and then we say, let's get ready for the future. So we can use this as generated adversarial networks to generate what the future looks like, future satellite images. Why? So we can work with city planners, so we can get peoples out of harm's way. So on the left of these images, you see the real images, but then on the right, we can really say, these are floods of the future. And I think, let's see, I can show you this actually I can show you this possibly in real time on the web. So let me, hopefully, is this working for you? Can you, maybe might be too much to ask it to go to the to the web. But I'll give you if you follow that link, all my slides are available. And so you can basically use this slider and you say, here's the real images of today. Here's what it'll look like for future forecasting. So I think this will be a very powerful tool to help people to not just give them the pictures, but to help with resilience and planning going forward. So we're really excited about this line of work in terms of how we can contribute, how we can help going forward. Okay, I'm checking my time here. Great, because I want to take some of your questions too. So I want to end on a discussion of STEM education, science, technology, engineering, and math, all within. And art and science has been studied in the similarities. But I've dedicated my entire career to STEM education. I think we need to change the discussion. I think maybe we've been having the wrong discussion. We need a lot more people, in the STEM fields. We need a lot more people to come to the table, the future of work, the jobs of the future. But how about this? Again, changing the conversation. We have to be inclusive. We have to bring everyone in. And surely it's not, if you're a parent or talking to my undergraduates, it's not about being the best in chemistry, calculus, and physics. I surely wasn't. It's about the problem and the passion. I get to think about sending people to Mars. I get to think about the challenges for climate. So it's really the exciting and the passion. How do we contribute to humanity? And guess what? Those chemistry and calculus, those are tools. Those are tools that I use. Those are tools that I use every day. Oh, you guys aren't seeing, are you guys seeing this? Oh, I gotta go back. Sorry about that. I think you're not seeing that. Okay, I was telling you about STEM education, but I was still on my flood images. So how do we have this conversation with folks to empower them and say, sure, I use calculus science every day, but that's not the important point. Not being the best in the class, it's just solving humanity's problems. That's where the passion comes from. That's a different conversation. And we need to bring everyone into that discussion. So I just call it no filtering people out. What problem do they want to solve? And again, as an educator, we have to empower them. And if it's in the arts, great. If it's in math, great. But it's my job then as an educator to tap into that, to say, we need everyone. We need everyone. That's how we're going to solve these big problems. So thinking about how we can change that conversation. And then I just want to acknowledge the science engineering workforce that many of you lead. This is, make no bones about it. This is a recent NSF, National Science Foundation study data. We're missing millions of people. This is just for the US statistics. We need 2 times the amount of women. If we want to reach parity, if we want to represent our entire society, for Hispanic and Latino workers in science and engineering, we have to triple the amount. And for Black science and engineering workers, it's more than double. It's more than double. So that's the work that we have ahead of us. So let's talk about it differently. Let's be innovative. Again, let's transform it. Let's think about how things that we haven't done in the past, incremental improvements, just are not going to get us there. We really have to think about different ways to do this. I think we can. I'm optimistic. And I want to end on a shout out, I guess, to my amazing heroine, Katherine Johnson, who's recently passed. President Obama gave her the Presidential Medal of Freedom. She's no longer hidden. Took, almost 80 years to tell her story, her and all of the Black women who literally got us to the moon, who did the mathematical calculations to get us to the moon. And I just had to put Andrea Getz up. Today was announced that she's a Nobel winner in physics, only the 4th woman in history to share the Nobel Prize. So, we're all out there. Everyone's all out there. And so hopefully we won't remain hidden anymore. It's tapping into everyone's amazing potential. As I say, every little person born, every little girl, boy out there is a superstar. But let's make sure that they're all invited to the table to work with us, join our teams, and there's a lot of work to do. But like I say, I'm optimistically looking forward to the future, when we have a much more inclusive, equitable, and we bring everyone to the table and all those different ways of thinking. So I thank you for your attention. That's the end of my comments, and we wanted to save time for some Q&A. There we go.
All right, folks, so please open your mics if you're a panelist, which there are quite a few of you, and we can have a conversation. Please ask questions if you have them. If for the guests, you have a Q&A function you can use. So we're very happy to pass your questions on to Dava.
Dava, I have a question, if I can just do that. This is Fiona, just to get people going. I'm curious, when you got to NASA, you found yourself in an organization that at some level has, I imagine, some great similarities with MIT, right? Full of people who are passionate about what they do and very technical, and lots of engineers. So that must have in some ways felt like home, and yet in other ways must have been incredibly different. What were some of the most sort of the moments of cultural dissonance and the things that you found both sort of different in a positive way and also different in a negative way that you were there to actually change?
Thanks, Fiona. It was, so that's exactly right. It was my peeps, my people being, technical, mission directed, mission oriented, but the bureaucracy, the 11 layers of bureaucracy was, of course, it, but now you're in a leadership position, and I can't blow that up. I can't change, the entire bureaucracy. What I had to do is say, well, how do I take, my skills and come to the table and help people think about things different. So the technical aspects of it, thinking about developing strategy for humans to Mars, that was great. But it was on the innovation piece, how can I nudge? How can I change culture is too big of an ask. But how can I celebrate people? They are incredibly innovative. Maybe they haven't been told that for a while. How do we frankly, just make it a yes zone, so that all the new hires that was part of the secret. All the new hires were so excited to be, they've been at NASA. I mean, they've been dreaming about these jobs. So how do we make sure to empower them and say yes? So you said up from the, A suite, from the administrator suite, saying, you are all here to innovate, to bring your best game every day. And maybe because they'd been there a while, somewhere along the way, they learned no, or they learned all the constraints. And so having that discussion about saying, how do we really just open it up? How do we, very small and discretionary funds, how do we open it up to tell people, bring crazy ideas, bring new thinking, have some discretionary funding, just to put that on the table to say, we want this discussion, as well as our safety culture, our mission oriented. And really we think that you can do both, but seeing how to, if I can say, kind of penetrate that bureaucracy. And it always starts with people. And so I say right off the bat, it just started with trust. It just started with the personal relationships, and then trust in terms of so that I could work with people and, again, bring in their ideas, understanding those previous barriers, but then moving on, because it seemed like they were kind of stuck. They could articulate what wasn't working, but then let's think about it differently. And we want to get to trying, and I learned this at MIT for sure, just try some experiments. And then when we celebrated and had an innovation day for the whole agency, guess who was in charge? We call them the leaders, the identified leaders who were within 5 years of hiring. So again, that's just what we do with the students. When you put those folks there and said, you tell us how we're going to celebrate innovation. What great ideas. So those were a couple of the challenges, but then a couple of the solutions as well.
Can I ask a quick question? For some reason, my question function's not working. I don't know what.
I think you can talk.
Okay, so I'm just going to talk.
For you.
Great talk. But one of the things I've learned about large organizations, that the people that are in best position to sort of disrupt them are ones that have lived in other organizations, that haven't necessarily grown up. So I'm curious, with your experience at NASA and at MIT, which one of those is easier to disrupt? NASA's been disrupted in a big way, but I can't think of a big disruption at MIT unless you can think of one. And, it's like, how would you change MIT if you could?
That's a great question. So I think we've been disrupted the last year pretty seriously. We've been rocked a bit. It's about, again, I would say it's about kind of continuous improvement, thinking about, who we are, taking a look in the mirror and say, who do we want to be? We're at MIT really comfortable with scientific and technical breakthroughs. And that's what we do every day. So we're very comfortable about that. But we're a people organization too. And so, again, how do we come together and think, how do we, again, move forward? So I think that that's the pretty big disruption, and leadership matters. Leadership really matters as well. In my experience in whatever organization, be it government, industry, or academia. And so leading by example, of course, modeling that behavior, and kind of putting yourself out there as well, like I say, and failing. Just even to students now, trying to get our heads around getting a little bit more comfortable with failing. This is, a lot of us here might be perfectionists, not used to failing. You haven't gotten to the positions you're at by failing. And so just opening that discussion up and having that discussion. I'm still working on myself in that regard too, but those are, again, just some thoughts. And disruption, change is hard, right? Change is hard. So you talk about disruption of organizations and people, we all, kind of maybe it's
so
hard.
Speaking
so
of that,
really,
I mean,
yeah, go ahead.
You were in NASA as it was going through this rather disruptive change. Like you said, the outsourcing of what I'm sure many of the longtime people at NASA thought was the heart of NASA. And so who were the champions within the organization? What was the profile that they had that, allowed the disruption to happen?
Well, to your point, some people coming from the outside, but most people, NASA's culture, there's very few folks coming from the outside. So it's really that working across. So some new ideas coming in, but I have to also want to acknowledge the lawyers and the financial people. Guess what? When some of the most innovative, creative people actually came from the lawyers, not all of general counsel, but you just need one. You just need one or two to say, how can we change these things? How can we change procurement? How can we still do it safe? But how can we do it much faster, much quicker? So again, I have to, in that sense, I have to say from within, you need a few champions. And we really need a few champions from both, from the chief financial officer, or let's paint a different picture. Sure, we've been doing it the same old way, but that's, we're not satisfied with that. And the legal, as well as, and I said, it's full of engineers and scientists, but it really was working across, especially legal and financial, and coming up with some different mechanisms. Let's say for innovation, when we did all that benchmarking and looked at that, we called it the solution mechanisms. The other thing was a lot of communication. So when we are benchmarking great ideas, it turns out if you work with NASA, if you're inside or outside, people typically know about three, how can I work with NASA? Okay, I can have a Space Act agreement. Okay, I can have a grant. I can have a flight experiment. People would typically know about 3 mechanisms. No, but there's 30 mechanisms. There's 30 mechanisms. So all kinds of, smaller programs, bigger programs. So we really had to say, no, there's just many ways to go about that. Let's just not get trapped into the only 2 or 3 ways we know how to do that. So that was also, a big part of moving forward, giving a lot of different options, a lot of different ways to, basically essentially different disruption, but different models that would work organizationally to move forward.
Dave, I think Cal had a question. So please, Cal, go ahead in case David didn't see you.
Yeah, so Dave, I only have, it was wow. I haven't had a lecture like this in a decade or more.
Is it okay?
And it was truly fabulous and very inspiring. I actually have 3 questions, and one is on Venus's atmosphere and the recent findings of sort of that, the potential for finding microbes in that atmosphere, and your thoughts on that. And so I thought that, that Venus being sort of a sister planet in another way to Mars. And then on Elon Musk, how is it disrupting NASA? So how is that backward disruption working? And just generally the difference between Boeing and SpaceX and their approach to disruption, and one being very different than the other. Not saying successful or not successful, but different.
So Venus, thank you for bringing up Venus. And it's, we need, so this is going to really accelerate. Super exciting. Again, those building blocks of life. So going to the Venus atmosphere. Now we know that Venus is a runaway greenhouse gas environment. It's already run the experiment. So I actually use Venus and Mars also to talk about climate. So people can say, oh, it's not an N of 1. It's not just Earth. We can study the planets, but absolutely accelerating with these new findings. Again, those building blocks, the chemistry for life in the Venus atmosphere. Plus, I'm a sailor. Can you imagine actually sailing through the Venus atmosphere? Essentially, literally sailing through. And another huge opportunity for international collaboration and cooperation, because the Russians are also Venus experts. Most missions, actually, who has the most missions to Venus is the Russian space agency. So I also look at it as soft diplomacy, what the world really needs now. Trying to figure out scientifically, can we work together? Can we communicate that diplomacy? So again, Venus, I think, is going to be right up on the top of the agenda, and getting a mission there quickly with all the other missions. But it is very high priority because its signs for potential life are so great. So you asked me about SpaceX and the disruption both ways, and it goes both ways. Took a lot for the government. And again, I was just on the team and a small player. I was a huge advocate, but it does literally take everyone. You have to have so many people in order to get these public-private partnerships and have that as the new organizational business model. But it's back and forth. As everyone probably knows, SpaceX has also had some accidents. They learned a lot, and they had to come back to NASA. They were empowered to have their own investigation reports, but always with NASA experts. And actually in that case, and FAA experts. So there's a lot of back and forth in saying that the culture of safety and mission assurance when it comes to spaceflight, now when it comes to human spaceflight, is absolutely critical. So a lot of back and forth in terms of opening up the NASA bureaucracy, moving faster, fixed price contracts, holding them to deadlines, but then the backward flow of information to ramp up the game when it comes to mission assurance and safety, and some really proven ways to go about those areas. So back and forth, making everyone better, which is great. People love that. And putting out the contracts to both SpaceX and Boeing for the commercial crew was really, really critical. Different price points, that's fine. Different businesses, different ways to get it done. But redundancy was really critical. And there's a lot of political pressure to go with one or the other. And so most of our time was fighting for the budgets to try to fund both. We want to fund, U.S. industry. We want to fund both, and having different organizations, different models, because they actually do learn from each other. And that is also competition. Competition is good. We want them both to be at the top of their game. They might have different approaches, which is great, but we want to see more. So to the cargo example, we had SpaceX, and then we had Orbital, ATK, which became Grumman, successfully flying, but also setbacks. It was an accident. And then we put Sierra Nevada, put them under contract. So it could be a third company also getting cargo up to space station. Again, competition is good. A completely different design when it comes to Sierra Nevada. It's like a 7th scale shuttle. So fly back up, especially for biological samples. Then you can fly your samples back to where you need them in the lab. So new contractors, new capabilities. So that's just some thoughts on that in terms of different organizations, different industries, from smaller companies to mid-sized to very large. But again, I think that they're competitors, but they're all learning from one another as well.
David, we got a question from our guest panel. I believe you mentioned that you were a scuba diver. How much did that influence your biosuit development?
Yeah, thank you. So just exploring underwater world and space. I always just say just different fluid dynamics, right? It's all exploring it. I love diving, and first of all, mostly appreciating the life, the biodiversity, but being scuba diving and freely floating, kind of how can you perform in, of course, usually wetsuits or dry suits. So it did, in that experience, definitely did inform some of the suit design to try to see. Also, if you're a scuba diver, we know how heavy and cumbersome the systems can be, and that's like going EVA in the space. So if you're going extravehicular activity, it's a planetary suit now for the moon or Mars, you know how heavy and cumbersome, and how kind of out of your center of mass is never right. You can get all tangled up when you're diving as well. And so those definitely inform us as an engineer and designer, thinking about how can we do this differently? How can we improve? Maybe continuous innovation. How can we improve, or how can we bring in a totally new technology to get the same job done? And our job's really important, both in scuba and for astronaut performance, is to keep the person alive first and foremost.
Dave, I have a quick question. Something I've been thinking about for a long time. I think this is a good time to ask you about it. So I was part of a tri-agency government organization with NASA, Department of Commerce, and the Air Force. And it was a gigantic cluster, fell apart, 3 McCurdy's, the NPOST program, I'm sure you know it. And I was always amazed by how impossible it was for interagencies to work together, how difficult it was. But yet you talk about something that's, I think, unique to the space industry or the space exploration industry, is this really close collaboration internationally that, doesn't matter what kind of necessarily diplomatic relations there are between countries. The space part of it seems to kind of sit apart from those whatever diplomatic issues might be going on at the time, to be really NASA. Can you maybe, as it relates to all these corporations that are listening in, that are international, almost all of them have a very international presence, what is it about that kind of that focus on the mission, or what did you learn about international collaboration that makes it so different than kind of the rest of the collaborations, and specifically about NASA?
It takes a lot of time, of course, to set up, especially international or just multi-organizational. It takes time. Actually, in terms of the NASA International Space, it didn't save any money, but it was the right thing to do. And so I think that's the important point, is we're going to get it done, actually, because we want to lead and say that this is international exploration. It is for everyone. It's not the domain of any nation, space agency. And so civil space is a great way to do that because everybody wants in. The science missions. Everyone wants to go to Mars and Moon. So it's really easy to get people's interest, and then different countries, and you might know the United Arab Emirates now has HOPE, the HOPE satellite going to Mars. So what they can afford, but guess what? NASA came on board, European came on board. They launched from Japan. So saying that, what a name, HOPE. I mean, that's for their next generation. So that message about we're better together, that we're better together. We can do this together. And also, I think it's a lot of trust and respect. So when it comes with again, human spaceflight, International Space Station, everyone knows the politics. The US and Russia and Europe are not doing well, but can we have one thing, getting that soft diplomacy? Can we have one thing that we have so much mutual respect across scientific boundaries, across technical boundaries? And at the end of the day, we're people, and we all have really, at the scientist level, the engineering, we just have a lot of fun working together. We have so much fun working together and learning from different people's expertise. So I think it actually probably starts around the coffee table, people wanting to work together, and then saying, we want to do this in the future of space exploration. The companies, it is global. And we just know that satellite services, it's global. Data, information, that's all global. So that's the exciting world we live in. I wouldn't want it any other way.
David, we have one other question, if you don't mind. Do you think that using future imaging techniques will finally be the thing that makes people understand and take action on climate change?
Boy, I wish. It's we're trying. I think it will help, but actually I need all the social scientists, all the folks from humanities. What changes human behavior? How do we change? We're living in a pandemic. We are living in a pandemic. So sure, we have all changed our behavior, some more than others. So the critical point is we can serve up the data. I'm going to make it beautiful, informative, and it's just science. It's no interpretation. But how do we then have that emotional connection? To me, it really is the compassion, the emotions. How does that make people react and change? So we don't have all the answers by a long way, being engineers, scientists. That's where we're really bridging and saying, please, we need other expertise. We're really relying on colleagues, teaming up with folks who study changing behavior. That's hard. That's much harder, I'd say, than the engineering and the technical parts of it. But the great thing is, again, looking for people who want to join and say, let's have this discussion, and leadership. And you have to give a shout out to Europe. Europe is leading in this in terms of leadership, in terms of sustainability, in terms of future. And so I hope that we can do our part as well. Individually, I think a lot of people are doing their part, but I hope we can do more when it comes to US policy very quickly.
Folks, other questions? I think we probably can squeeze in one more if anybody has one.
It's Steve from JP Morgan.
Oh.
No, go ahead.
Steve, go ahead. No, you might.
So I had just had a question from a corporate standpoint. As you're thinking about innovation and breaking, through barriers of innovation, how do you sort of wrestle with keeping the momentum of some of these ideas when you have shareholders and CEOs and CFOs and other people in the organization whose attention may shift or change based on your success or failure? How do you keep that momentum going?
Yeah, great question. Great question. That's probably where a lot of the efforts run out of momentum. Getting on point to the champions, just not the leader, not just the CEO leadership, but having champions in the organizations. First, empowering some folks, but you need the folks who are on it, because it could easily, with the way other priorities take precedence. So I think that also the portfolio of investment on what we call them the low TRL technologies, keep them going, because once they're starved or shut off, when you lose the momentum, that restart is very difficult, and that's where I think a lot of things atrophy. So great question. I definitely don't have all the solutions, but just in terms of trying to have that mixed portfolio, trying to have some of those lower TRL bets when it comes to technology, and making sure to have those champions. That's, I think, really important. So a lot of that work gets done in different organizations in terms of the technical fellows and different people like that, having your skunk works, having things that you can keep the progress going. That's a little bit more from the technical side. How you do the business model disruption. You're going to hear from Fiona next, and she knows much more about that than I do.
David, can you take one more question? I think Thomas
Sure.
had one. Thomas, go ahead, please. Thank you for your
All right.
patience.
So you showed your innovation model earlier in the presentation. I was wondering how your day-to-day operation looks like. So are they all 4 of them are separated, or is it one unit? Can you talk about that a little bit?
That's a great, again, that's really kind of the portfolio and mapping. And so that's why I start with the bottom and say continuous, and just right up front acknowledge that's 80%. So that's where most of the work happens. That's the daily work, and it just consciously trying to ask, can I do it differently? Can I do it better? How can I improve? But not a lot of disruption. So kind of starting there, and then just saying, what's the right investment? What's the right investment for your company in terms of the technology push? That's some part of the portfolio. I always hope it's not single digits, 1%, 2%. I actually encourage people to, again, have that be much closer to 10% or more when it comes to, again, the people part of it. So it really is tracking all of them, but I do look at it as a portfolio, and probably the fewest investments in the transformative, really the hard stuff that's to do. You want it on the table, but the concentration is going to be with the majority. I guess the Pareto front, the 80-20 rule, to kind of map that out and split up the investments.
Nice. Thanks.
So David, we had a comment that you may or may not be seeing. Travis, do you want to just mention it out loud so David doesn't have to try and read
Yeah,
this
happy
tiny
to.
chat?
I just wanted to say I had so many questions, but I know we're limited in our time. But David, I so much respect and admiration for what your career and your example, as what I said in the comment, was a full spectrum innovator. Like, you have innovated across technologies, you have innovated across organizations. And I love the personality and passion that you bring to it, even the way you ended the talk on STEM and just saying, hey, let's focus on passion and problems. It's so simple, it's so clear, it's so inspiring. We need many, many more of you. So thank you so much for taking the time to share your example with us this morning.
Well, thank you all.
David,
It's a pleasure.
David, thank you so much. It's been a pleasure. And
Thank you.
sorry, we're all in a room where we can't clap at you, but we'll clap at you on the screen. We really appreciate your time. And thank you. Any other last minute thoughts or questions from anyone before we let David go? It's been an absolute honor to have you, and we thank you for that. Thank you.